Assalamualaikum warahmatullahi wabarakatuh. Hello dear students, this is me Asif Javed. I welcome you on my YouTube channel Maths Quest. In today's lecture, I will talk about a very important topic in numbers theory, which is called as Wilson's theorem. What is this Wilson's theorem? Let me tell you something about this theorem. Say that prime number n minus 1 factorial minus 1 prime numbers we have either prime or odd primes. Yes, a given prime we have only one prime number, that like this. Talking about p equal to minus 1 factorial minus 1, which is true. Why? Because if you will put here 1 factorial, it's clearly congruent to correct, because divides 1 minus 1. For odd prime, we know that all other primes other than even prime number, they are all odd primes. So what if A is odd prime? These odd prime, this clearly says that B minus 1 is even. B minus 1 is even. Now we have certain things that we have done in our course of ring theory. Here we studied that this set ZB, this ZB which is equal to 0, 1, 2, and so on, B minus 1. This is a field structure. This is field. What does this mean? In case of field, every non-zero element has a multiplication the same field. This is clear that non-zero elements of 1 to 3 minus 1, they will have multiplication numbers. They will have multiplication in Z. However, if you look at congruence, x square is congruent to 1 model of B. Let us look at this congruence, which is x square minus 1 is congruent to 1 model of B. This is a congruence of order 2. This is a congruence of order 2. And Lagrange's theorem says that if you have a congruence of, sorry, not order, degree, if you have a congruence of degree n, then you can have at most n solutions for that congruence. Since we have this congruence of order 2, so Lagrange's theorem says, Lagrange's theorem suggests, what does it suggest? It suggests that it will have at most 2 solutions modulo P. And what are those 2 solutions? If you put x equal to 1, so if you see carefully, x equal to 1 will satisfy this, because 1 square minus 1 is congruent to 0 modulo p. If you put x equal to p minus 1, again this will become p minus 1 whole square minus 1, which is equal to p square minus 2p plus 1 minus 1. So p square minus 2p, which can be written as p into 1 minus uh, p into p minus 1. So again this is divisible by p, so this will also satisfy this. So exactly it will have two solutions, because at most it had two solutions and we have found those two solutions. One is x equal to 1 and one is x equal to p minus 1. So what we have been able to prove is that, see carefully, what I essentially mean is that I mean to say that x equal to 1 and x equal to p minus 1, they satisfy this. And you must have done in your course of algebra that whenever, let us not consider this modulo p sort of thing. If we simply consider any group, multiplicative group, and if you have a square equal to 1, that is identity, then you say that a into a is equal to e, or inverse of a is equal to a. So whenever the square of any element is equal to identity element, this suggests that the element is self inverse of itself, or we say that the inverse of element is equal to the same element. So what we have been able to conclude from the discussion so far is that 1 and p minus 1, they are going to be, they satisfy this equation. So 1 square is congruent to 1 and p minus 1 square is congruent to 1, or you can write it as 1 into 1 is congruent to 1, p minus 1 into p minus 1, this is also congruent to 1 modulo p. Okay, that means inverse of 1 is 1, inverse of p minus 1 is p minus 1. So these are the only possibilities. These are the only elements from the set ZP, from the field ZP, which are inverse of themselves. So all other non-zero elements, they will be also, they do will have multiplicative inverse, but the multiplicative inverse will be a different element. I mean to say, as I had ZP and I had non-zero elements from 1 to p minus 1, and as I took p as odd, so p minus 1 was even. P minus 1 was even. So total number of elements from 0 to p minus 1, they were even. Fine. Now what I am doing here is that I am not concerned about 0. Why I am not concerned about 0? Because I am talking about non-zero elements. I am talking about non-zero elements. So p is odd, p is odd. So p minus 1 is even. P minus 1 is even. That means elements from, I mean to say, 1 to p minus 1, they are even. If I count from 1 to p minus 1, this is even number. Now out of these even numbers, two numbers, that is 1 and p minus 1. These two numbers are self-inverse of each other. That means the inverse of 1 is 1 and inverse of p minus 1 is p minus 1. So if this is from 1 to p minus 1, we have even numbers. And if I talk about from 2 to p minus 2, if these are evens and I am taking something, if I am taking 2 out from even numbers, again we have these elements from 2 to p minus 2, they are even in number. That means if I take elements from 2 to p minus 2, they are even in number. If you see carefully, what will happen here, since we have even number of numbers here, so they will form pairs. And as I told you that since we are working inside the field ZP, so every non-zero element must have a multiplicative inverse inside ZP. That means we will be having pairs. 2 will make some pair with some other element, suppose some other element B, such that 2 into B is equal to 1. Again, this 3 will make pair with some element suppose C, such that 3 into C is congruent to 1. So every time we will be having pairs, and all these pairs are going to generate element which is identity element. So this will look like 1 into 1 into 1 into 1 modulo P, because all these pairs are going to give us identity element of ZP. So what I have been able to conclude so far, if you have followed me carefully, if you haven't followed me carefully, then you can actually uh, rewind the video. You can go back in the video and look what I have said so far. So from 2 to P minus 2, this is congruent to 1 into 1 into 1 up to P minus 2. This will also be having some pair. So all these pairs will give us this. Now what you will do, you can actually write 1 here, it will not affect. This is P minus 2. This is, if you also attach P minus 1 here, this will be congruent to 1 into 1 into 1 into 1. This is going to be 1 into P minus 1 modulo P. So from 1 to P minus 1, this is called P minus 1 factorial. This is congruent to P minus 1, and this P minus 1 itself is congruent to minus 1 modulo P. So indirectly, P minus 1 factorial is congruent to minus 1 modulo P. Why is this P minus 1 congruent to minus 1? You can see it clearly because this P divides P minus 1 minus minus 1. So this is P divides P minus 1 plus 1. So P divides P, therefore P minus 1 is congruent to minus 1 modulo P. So we have been able to show that P minus 1 factorial, this is indirectly congruent to, because we have transitive sort of relation, this is congruent to minus 1 modulo P. So even if P is odd prime, still this result is true. And this result is known by the name Wilson's theorem. So I hope that this theorem is clear to one and all. Thank you so much and have a nice day.